Hello everyone, I'm Mason Fidino and I'm going to be talking about a project I've been working on with some wonderful collaborators out of the University of Rhode Island on how one should actually quantify how species may modify their diel activity in response to habitat change. But before we get there, I think it's actually important to take a step back first and ask, what is habitat to a species? Historically, it's been defined as the place where an organism lives or the place where one would go to find it. However, I feel this definition lacks a lot of nuance that we need. For example, if you went out to a forest to potentially see, or more likely hear, say a Cooper's hawk or a great horned owl, the time of day you actually visit that forest is going to have a pretty huge influence on the likelihood of hearing either of these species, given that one of them is nocturnal. As such, some more recent definitions of habitat are explicitly acknowledging the importance of time. For example, habitat is a description of a physical place at a particular scale of space and time where an organism either actually or potentially lives. Yet, when we actually start modeling what a species habitat is, we basically ignore the role of diel time. Certainly, there are a multitude of statistical methods that now exist that do a really awesome job predicting species distributions across space and even over large timescales, such as differences in a species occupancy pattern between seasons, but they don't really do a good job of telling us what time of day a species may be most active within a given habitat patch. Instead, we rather unfortunately have to analyze diel time separate from a species distribution. Oftentimes, this is done using the overlap package in R. Unfortunately, to compare spatial variation in a species diel activity pattern with this method, it actually forces us to use habitat categories instead of continuous gradients. And more often than not, these categories are not helpful. For example, if I said I compared a species activity pattern in urban and rural areas, what comes to everyone's mind here for what urban and rural is will no doubt be colored by the city you live in. The urban core of Chicago vastly differs from New York City, from St. Louis, or from Seattle. As urban ecologists, we've known for decades that we should be using continuous gradients to better reflect patterns of urban intensity, yet when we're trying to, say, compare diel activity patterns in urban and rural areas or across a gradient of urban intensity, the overlap package forces our hand, and that is not good. We don't want to use these categories, but we have to because that is what the statistical method requires. On top of this, packages like overlap completely ignore the notion that species are imperfectly detected on the landscape, which could potentially add substantial bias to statistical comparisons if left unaccounted for. On top of this, as urban ecologists, we know that anthropogenic factors can affect both when and where a species is active. So really, we should be modeling these things together. We know that along gradients of urbanization, species occupancy patterns or an abundance often change. We also know that species modify their diel activity across gradients of urbanization. So really, we should be trying to fit both of these factors into a single statistical model. And you know what? It's actually not as hard as you think. For one reason, we already have access to really fine scale spatial temporal data that we'd actually need in order to modify how a species may change their diel activity due to habitat change. On top of that, we already have the modeling framework in order to do this. It just needs a little bit of tweaking. In 2016, Chris Rhoda et al. Came out with a really cool paper of a single season occupancy model that lets you estimate potential interactions among species. And a couple years later, I generalized that model out to accommodate multiple seasons of data. And these models, if you're unfamiliar with them, are multi-state occupancy models. I'm already assuming at this point that everyone here has a general working knowledge of what an occupancy model is. If you don't, go ahead and just pause this video and Google it and come right on back. So, multi-state occupancy model for multiple species, you basically segregate states based off of the community that was detected. So, for if you're modeling the distribution of two species, you have four potential states. The probability of occupancy that a site is not occupied, the probability that species A is there, in this case a cottontail rabbit, the probability that species B is there on its own, in this case the coyote, or the probability that both species are present within a single habitat patch. And what's really cool about this then is that we could, quantify effects on whether or not, say, the occupancy of cotton-tailed rabbit is lower in sites that actually have coyote. So here's the trick that I'm going to let you in on. You can actually segregate states in such a model in any kind of way that you want. So, for example, if we actually segregate states based off of time of day, we could break the sort of occupancy of a species of a single species, mind you, into four separate states. So the probability that a site is not occupied, the probability that the species only uses the site during the day, the probability that a species only uses a site at night, or the probability that a species uses a site during the day and the night. So we're discretizing the diel behavior of a species. And when we do that, all of a sudden, this becomes what we are calling a multi-state diel occupancy model. Pretty cool stuff. And MSDOMs can still tell you the same exact thing if you wanted as a standard occupancy model. You can just do that by basically summing up different states to generate what are called marginal occupancy probabilities. Say, for example, if you sum up the probability that a site's occupied during the day, the probability a site's occupied at night, or the probability a site is occupied during day and night, that just represents the occupancy probability overall of a single species at a single site. But we can also calculate conditional probabilities as well, which is a really unique feature of this class of model. For example, we could calculate the probability that a species uses a site at night given the fact that they are present, which represents either selection for or against using a habitat patch during a certain time of day. And unlike analyzing diel data with, say, the overlap package in R, we can actually incorporate continuous covariates into these probabilities and assess these changes over gradients of urbanization instead of using urban and rural categories. And with that, let's apply this model to some data and see how it actually works. For this specific example here, we're going to assess whether or not coyote alter their diel habitat use across an urbanization gradient, specifically in Chicago. The coyote data that we have comes from a large-scale, long-term camera trapping survey that we've been conducting throughout the greater Chicagoland area since about 2010. We sample 4 times a year in January, April, July, and October. And whenever we go out to set up cameras, we leave them out for about a month at a time. And while we've been sampling since 2010, I'm only going to be analyzing data from 13 primary sampling periods between July 2016 and July 2019. And right above me, you can see these are our sites, the little white dots that we've been sampling for the last decade. We place our camera traps in urban green space throughout Chicago. That, for the most part, is golf courses, city parks, natural areas, or forest preserves, rather, and then cemeteries. To represent the urbanization gradient within Chicago at each of our sites, we calculated the percent tree cover, percent impervious cover, and then the housing density in units per kilometer squared within 1 kilometer of each study site. Because these are all horribly correlated with one another, if you're in a parking lot, you're not in a forest and vice versa. We applied principal component analysis to these covariates and generated a single sort of urbanization score for each site. Negative values of this PCA term indicate areas of high tree cover, whereas positive values indicate higher impervious cover and increased housing density. Again, as a reminder, so we discretized the diel states that we detected coyote with our camera traps into 4 different categories. So no use, day use, night use, and then day and night use. For this case study, we fit 2 models to the coyote data. The first one was a dynamic multi-state diel occupancy model that included that urbanization metric on all of our logit linear predictors, colonization, extinction, etc. We also compared it to a standard multi-season occupancy model, so basically just estimating whether or not the species is there over time, that included that urbanization metric. And then we compared all these models using the conditional predictive ordinate, and we fit these models in JAGs via runjags in R. This slide here just shows that the multi-state diel occupancy model we fit greatly outperforms the standard multi-season occupancy model. So let's take a look at these results. So this dynamic model has a whole lot to unpack with it. Because we have a 4-state model and we're estimating colonization and extinction among these states, we're actually estimating 16 different transition probabilities. So for example, if you are in state, let's say, no use, we need to estimate the probability that you move to each of the 4 different states from one season to the next. So the probability that you move from state no use to no use would actually be located right here. Or the probability that you move from, let's say, night use to day and night use would be right here. I'm not going to go through all of these, but I'm just really trying to signify here that things can get pretty confusing pretty fast when you're trying to fit this dynamic class of model. However, and it's really important to note here, there's lots of ways to simplify this. You can actually take that 4x4 transition probability matrix, which is a Markov process, and compute the expected occupancy of each of your states. I'm only plotting out 3 of them here. On the x-axis, we have urban intensity, whereas on the y-axis, instead of transition probabilities, we've got probability of occupancy of these 3 separate states. So at low levels of urban intensity, we see that the night and day use is the most likely state for a site to be in, whereas at very high levels of urban intensity, we see that night use has slightly become the most likely state. But we're not done yet. We can actually take this one step further and compute the probability of selection of these different diel states with these conditional probabilities on the left. And what this actually shows is that as urban intensity increases, coyote, who previously were basically using sites during the night and the day, are beginning to partition their habitat use and are either predominantly using sites either solely at night, or at sometimes there's some specific sites that they're using during the day. And of course, if you wanted to look at this with overlap, you can actually do that after the fact. And so I'm comparing on the right here activity patterns above sort of an urbanization value of 1.5. That's the threshold that I identified on the left here. 2 sites that have an urbanization value less than 1.5. And you can see here certainly that this blue line, higher levels of urbanization, there's much more night use and there's slightly more day use as well. And so this is actually lining up with what our model is predicting. Pretty cool. So why would you want to use an MSDOM? First and foremost, it actually allows you to address hypotheses on a species' spatial and diel habitat selection all within a single modeling framework. No other modeling frameworks allow for this right now. Second, because we're discretizing the diel state that we observe, diel activity, it actually allows us to look at these changes over continuous gradients, like urbanization gradients, as I showed you with the coyote analysis. And then finally, we can actually use this model to identify thresholds where a species theoretically switches its diel states. No other techniques can do this right now. And the current analysis I showed you today was already done with data in hand. If you're actually thinking about using this model, you could theoretically collect additional data to actually allow for really fine scale explorations into a species' diel habitat selection. So say, for example, if you put out a passive acoustic monitor, you can incorporate urban noise, light monitors for light pollution, you could monitor local weather or add more cameras for human activity. The possibilities are endless. And with that, thanks for listening. You could follow my colleagues and I on Twitter at LPZ_UWI. Thanks.